Okay, so complete the chart by writing the domains and range of each function type in terms of h and k. So for this one, what is the domain and range? So for a square root, what is the domain and range? Well, the domain is going to be my x values, right? The domain is going to be h to positive infinity. So it's whatever the h term is, to positive infinity. My range is going to be from k to positive infinity. If my a is less than 0, it's going to be from negative infinity to h. And my range is going to be from negative infinity to k. Okay, domain and range for cubic functions. We've got negative infinity to positive infinity, negative infinity to positive infinity, and same thing for when a is less than 0. Same one. So cubic root functions are pretty easy. Talk about identify information about radicals and contacts. So kind of similar to what we were talking about yesterday. So altitude. On Earth, the distance d in kilometers that one can see the horizon is a function of altitude, a in meters, and can be found using this formula. But before we even look at the question, we want to look at what did they just define. They said d, which is the distance in kilometers, and then they said a is the altitude. To find the corresponding distance to the horizon of Mars, the function must be stretched horizontally by a factor of about 9/5. Okay, so if someone is at altitude of 100 meters, what is the distance on the horizon on Earth? And then what is the distance to the horizon on Mars? So this function right here is for Earth. Okay, Mars is going to be a little bit different. So first, let's take this equation, okay? And what are we going to put 100 at? Where are we going to put the 100? We're going to put that 100 meters. It's altitude, right? So which variable are we going to put it in for? D or A? A. Okay, so we're going to plug in. So we get 3.56 square root of 100. Well, we know the square root of 100. That's 10, right? So we're going to do 3.56 times 10, which is going to give us 35.6. This is in meters, and we've got to make sure that we convert it into kilometers, right? So remember how to convert from kilometers into meters? Okay, so remember the little acronym thing that you use to memorize it? King Henry died by drinking chocolate milk. Y'all heard that before? No? Dang. Okay, so what you'll do is we'll start with meters. We want to move to kilometers. So we want to move over 1, 2, 3. So we're going to take the decimal point and move it over 1, 2, 3. So our final answer will be 0.0356 kilometers. So they said that what is the distance to the horizon on Mars? We're going to take this function, but they said that it's stretched horizontally, okay? This direction is really important. Horizontally means that we're going to impact what's inside the radical. So we're going to write the function for Mars as 3.56 square root. And when we're stretching horizontally, which vertically is going to be very different, but if we stretch horizontally, we're going to flip this fraction and put it inside. So if it's horizontal, then you're going to flip the fraction. If it was vertical, then you're going to leave it outside and leave it however it's written already. So now we can plug in that 100, right? So we got 3.56 square root of 5 divided by 9 times 100. So this is going to be 3.56 500 divided by 9. And when we plug this into our Desmos graphing calculator, because I'm not doing that in my head, (3.56) square root of 500 divided by 9. That's going to give me 26.53. Right, so again, that's going to give me 26.53. Now we do have to convert this into kilometers. So again, King Henry died by drinking chocolate milk. And we're going to move this over 1, 2, 3. So we're going to move the decimal over 1, 2, 3. So this is final answer is going to be, I'll write it up here, 0.026 kilometers. And just as a side note, think about this logically. Mars is about half the size of Earth. So it kind of makes sense when we have the distance to the horizon on Mars is going to be a little bit shorter than it would be on Earth. Yep. That's what I just looked up. Mars is about half the size of Earth. That's what it says. I didn't know. Now we know. Yeah. How does it go? It's like, okay, so here's the sun. What's the next planet over? What is it? Okay, and then it's, but Mars is behind us, right? Or is it in front of us? Okay, so it's Mercury, Venus, Earth, Mars. Look at me pulling out that 4th grade stuff, right? Listen, I'm gonna win Jeopardy one day. It's fine. Y'all ever play Jeopardy before? No. Oh my gosh. Okay. 7 o'clock every night. Huh? Oh, okay. All right, so special airbags are used to protect scientific equipment when a rover lands on the surface of Mars. On Earth, the function is f of x equals the square root of 64x, approximates an object's downward velocity in feet per second as the object hits the ground after bouncing x feet in height. The corresponding function for Mars is compressed vertically by a factor of about 3/5. Write the corresponding function for Mars and use it to estimate how fast a rover will hit Mars' surface after a bounce of 45 feet in height. So, one, coming back up here, because that was a really long paragraph. Okay, we see the function. Okay, and this is on Earth. So you'll have to pay attention to like what they're actually talking about. Now, it's talking about velocity in feet per second. So that's what f of x is. And x is going to be feet in height. Okay. Now, on Mars, it's compressed vertically by about 3/5. We're going to write the function for that. So we're going to rewrite this. And we're going to put that 3/5 out front because it's compressed vertically. Now they want to find how fast a rover is going to hit the Mars surface with a bounce of 45 feet in height. So if we take 3/5, multiply it times 64, and multiply that times 45, that's going to give us our velocity. So 64 times 45 is going to give me 2,880. And then if I take the square root of that, that's going to give me roughly 3/5 times roughly 53.6656. And 3/5 is 0.6. So this would be a velocity of 32.19. We're going to say 32.2. And it's going to be feet per second. Okay, so that covers about from here to that wall in 1 second. That's going pretty fast. You're faster than that? Okay, so the speed S in miles per hour that a car is traveling when it goes into a skid can be estimated by this formula, where F is the coefficient of friction. Okay, I'm sorry, big F. Little f is the super elevation, and d is the length in the skid marks in feet. So that's a lot. I'm going to highlight the important parts. The equation, F is the coefficient of friction, little f is the super elevation, and d is the length of the skid marks in feet. Okay. After an accident, a driver claims to have been traveling the speed limit of 55 miles per hour. The coefficient of friction under the accident conditions was 0.75, and the super elevation was 0.05. So you know when like people get in car wrecks and they're like, I didn't do anything, it was them, blah, blah, blah. And you're like, try to figure out like whose fault it was. Just me. Thanks, guys. Okay, so what you do is you actually look at the skid marks. If there's no skid marks, that means that they weren't trying to brake. Which, does that make sense? Like they weren't, skid marks are like the rubber is tearing off of the tire, right? So, right. So you try to figure out who's at fault without having seen the accident. And so you actually use this equation in order to do that. Okay, so this is where math can be kind of helpful. Lawyers have to use this equation. Lawyers. Like when you sue people, you got to figure out like whose fault it was. Were they actively trying to stop? Were they not trying to stop? Especially when like people end up not making it through an accident. Definitely. So the question is, was the driver actually going 55 miles per hour? Okay, so how can you prove it? So we can use this equation to help us. We got S equals 5.5. Now, what was D? D was the length of the skid marks, right? Did they tell us that? Did they tell us what D was? I don't think so. We're going to leave that alone. Did they tell us what big F is? F is the coefficient of friction. Yeah, they told us it was 0.75, right? We're going to go ahead and plug that guy in. Did they tell us what little f is? Yeah, the super elevation was 0.05. And then did they tell us what the speed was? Okay, we're going to assume this guy was going 55, right? So it could be like 55 is equal to 5.5 square root of d times 0.75 plus 0.05. Okay, hey friend, you good? Okay. All right, so now we're going to solve for d. What was d again? Okay, look at the word problem right here. Is the length of the skid mark. Okay, so how would that be helpful? Again, we're trying to prove that this guy was going 55, right? So we could measure the skid mark length. We go out there and we could measure it. Okay, so now we're going to solve. So we want to get d by itself. It's attached to this 5.5. So we're going to divide by 5.5 on both sides. So when we take 55 and we divide it by 5.5, we're going to get 10. And now we still want d by itself, but it's underneath the square root. So we're going to square both sides. 10 squared is going to give us 100. And then we have d. And let's go ahead and combine 0.75 and 0.05. That's going to give us 0.8. And so now we're trying to get D by itself. So we're going to divide by D. I'm sorry, we're going to divide by 0.8. And so D is going to equal 100 divided by 0.8, which is 125. This man skidded for 125 feet. So let's think about that. Okay, normal cars are about what, 10 feet long? Roughly? Yeah. I mean, he could have slowed down. But that's if there's 125 feet of skidding, right? Mm-mm. Okay, so if you are trying to stop, you want to think for every 10 miles per hour, you need a car length between you and the next car in front of you. You need one more car length for every 10 miles per hour that you're going. So roughly, that's what that is. Yeah. Now we would have to actually like go out and measure the skid marks. We would have to measure 125 feet. That would tell us whether or not he was actually going 55 miles per hour. But you know how people be lying. They're like, yeah, I'm going 55. And like, bro, you were going 95, right? Like, be like that sometimes. Okay. We're going to do a little bit of practice on this stuff, and I'm going to post it up on the board. You are going to write it in your packet. Okay. The only way to get good at this stuff is to practice, because I know like we don't like word problems, but it will be helpful. So it says the speed of sound in meters per second is described by this equation, where H is the ratio of specific heat and T is the temperature in Kelvin. Find the temperature when S equals 340 and H equals 1.4. Okay, so we got equation. Nope. We got equation. We've got H is the ratio, T is the temperature in Kelvin. They tell us H is 1.4 and they tell us S is 340. So basically, this is just plug in, right? Okay, so let's try it. S is 340, square root of 286. H is 1.4, and we're trying to figure out the temperature. Okay, so if we multiply 286 times 1.4, we get 400.4 T. If we're trying to get T by itself, we're going to square both sides. So if we take 340 and we square it, that's going to give us 115,600. And then we're going to divide by 400.4 on both sides. And so T is going to be 288.7. That's like real, that's real high. One thing to always pay attention to is making sure that your units are measured in the same thing. All right, so in order to complete America's Cup sailboat race, a boat must satisfy this rule, where L is the length in meters of the boat, S is the area of the sails, and D is the volume in cubic meters of water displaced by the boat. If a boat has a length of 20 meters and a sail area of 300 square meters, what is the minimum allowable value for D? Okay, so all we're going to do is we're going to plug in and solve. Okay, so the length is 20. S is going to be the area. And then we have D. Okay, so we'll pick this up tomorrow.